Let us begin with a word of prayer. I'll start. Heavenly Father, we thank you for this day. We thank you for this opportunity we have just to meet together again and study lead groups. Just pray that you just bring understanding to us as we discuss these things together. Lord, in your name I pray. Amen. Well, as I have mentioned to one of you, I spent the better part of this weekend preparing zounds and zounds of linear algebra notes. I have not had a chance to fix my various transgressions from last time. I will have to work on those. Hopefully I will fix them at some point. Although I have a suspicion that as I read your homework, that will help me on that point. So I talked to Bill, my brother, about this general problem we have. Like, when is a group simple? And I kind of mentioned to you guys last time. I was like, oh, maybe we're going to learn, about Lie algebras, and then it'll be simple in the untechnical sense, reasonably uncomplicated to check whether the Lie algebra is simple or not, because that's an algebra problem. And algebra is a vector space of multiplication. It's not so bad. And so Bill kind of threw some water on that. He's like, well, that just Lie theory just gives you information about Lie subgroups. Doesn't give you information about other kinds of subgroups. And you see Lie subgroups are the continuous ones. But you could also have discrete subgroups. And Lie theory may be silent on that point. So I was very encouraged as I was reading chapter 3 this week, and I came across, I will jump straight ahead. I have no right to read this at the moment. But at the end, like section 3.8, which is a little bit ahead of where we are at the moment, he gives this result, the centrality of discrete normal subgroups. And in this theorem by Schreier from 1925, it says if G is a path-connected matrix Lie group with discrete normal subgroup H, then H is contained in the center of G. All right, so today we're going to study the center of groups, among other things. Before that, we'll study these maximal tori, which will give us a tool we need to understand centers, following the great mathematical physicist Weil. But anyway, there's just a little proof on page 70. I'll go through it later, maybe. And it proves it using just basic continuity arguments, not a hard proof. And so that's pretty cool, because that means that all the discrete groups have to be stuck in the center. Well, we can calculate the center, right, for these examples, and so if they're path-connected, and we'll also argue that today, that these are path-connected groups, then we'll in fact, it looks to me, unless I'm missing something, recover a separate proof that, as he says, in particular, SO2m plus 1, so not just SO3, but SO5, SO7, SO9, so forth and so on, forever and ever. They have no non-trivial discrete normal subgroup because its center is 1. So then you only have to worry about continuous subgroups, in other words, the Lie subgroups, which we'll deal with through other methods later.
What about non-path connected groups?
Then my brother's derision for my idea is probably well warranted. But we're living in a fairly small universe of examples here right now. We're just looking at these classical matrix groups, so maybe we can say something nicer. Okay. So I thought that was an interesting little discussion. Hopefully we will make more sense of it as we go on today. All right, so I introduced to you guys last time the idea that we have SON. How's it go? So basically here's the story. With Rn, with the dot product, we have S. We have ON and SON as the isometries that fix the origin, right? And the isometries which fix the origin and are orientation preserving. And then for Cn, with respect to the complex inner product, we pick up what? We pick up the unitary matrices of order n. And for the ones that are, not disoriented, the ones that preserve the orientation, SUN, right? And we even said for HN, for n-fold copies of the quaternions, quaternionic n space, we pick up what? Yeah. I don't know whether I'm not sure which column SPN should be put into. So here.
Isn't it both? Oh no.
Hmm. I don't know. I only see discussion of SPN, so apparently, as is the case, as is often the case as we talk about things with quaternions, they kind of belong, but kind of don't. So anyway, these symplectic, I guess that's the contribution of, how do you say it, Chevrolet? Claude? How do you say it? I don't know. Oh, and here I am. I never do solve my how to keep my book open problem. Oh, here. Ha 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 ha. Take that. Ha. Okay, sorry. I may be a little bit too excited about that, but I'm not sure where this belongs. But anyway, definitely belongs with HN, but other than that, I'll just kind of do this. All right. Again, you can understand. And okay, so, but more specifically, if we had A an element of ON, what does that mean? A transpose A is equal to the identity, right? And if A is an element, so then if A is also an element of SON, that means that the determinant of A is what? 1, right? And again, if A is unitary, what do we have?
A transpose A bar.
Yeah. A conjugate transpose A equals to the I identity. And then, of course, if A is also in SUN, that gives us the additional condition, the determinant of A, although I don't usually use A here, I usually use U, is equal to 1. All right, so just some observations that we should make about these things. Columns of A in ON form orthonormal set. In the sense that if you look at A transpose A, right, and look at the ijth element of that, right, what is that? Well,
It's going to be Kronecker delta.
yeah, it's Kronecker, exactly. It's Kronecker delta ij on the other side because it's the ijth component of I. But on the flip side, this is what? This is exactly the ith row of A, right? Well, I'm sorry, it's row I of A transpose dotted with column J of A,
Right.
which is to say that it's column I of A dotted with column J of A equal to Kronecker delta ij. So that is exactly the condition you need to have that the columns of A are orthogonal, and also they have length 1. Right. So they're orthonormal, in fact. Say, well, shouldn't you call it an orthonormal matrix? This is a legit complaint. But, oh well, this is what we have. Orthogonal sets, of course, don't have you could have a scale factor here, right? But anyway, it is the language we're stuck with. On the flip side, what do the columns of a unitary matrix look like? If you look at this condition, you've got U conjugate transpose U is equal to I, right? So what this says is basically column I of U conjugate dotted with column J of U is equal to Kronecker delta ij. So that is exactly the orthonormal condition with respect to the complex inner product, where we take the conjugate of one vector and basically dot product with the other. That was the complex inner product. Okay. And we'll come back and talk about this one separately when the time is right. There's details here. It's also going to be orthosymplectic in a certain sense. So let's talk about path connectedness. And there's an interesting point here that I just think is so interesting. And I'm kind of disappointed in myself for not thinking about this more before I read this. And just difference between how we think about rotations and how mathematically and how we think about them, you know, say physically. If somebody tells you they rotate a door, right, 30 degrees. Now, mathematically we think like this. All right, close your eyes. Open them. Okay, 30 degrees, right? It's there, then it's here, right? But physically, rotating a door 30 degrees looks like this. It's a continuous range of motion, right? So the physical notion of rotations has this, it already has this kind of like path connectedness built into it. It's got this continuous rotation from one state to another, you know? That's what he says. He says, in everyday speech, a rotation is a movement through a continuous sequence of positions. So it corresponds to a path in SON connecting an initial matrix 1 to a final matrix A. All right. So let's start by looking at, so we're going to give an argument that SON is path connected. Let's look at that. Let's look at that theorem. Okay. Let's see here. So theorem SON is path connected. All right, so so many colors to choose from. Oh, wait a minute. What are you thinking?
And
What's that?
did we prove in the homework that O3 is basically equal to SO3, or that there's nothing in SO3 that's not in O3?
Oh, SO3 and O3 are different.
They're different?
Yeah. So O3,
Also has reflections.
right.
That's the one.
Yeah. Trying to think of a correct way to say it. I mean, I want to say that O3 is twice as big as SO3, but
Well, I was just thinking about the implications of the homework.
but
But
no, they're different. How about this SO2? So what's SO2 look like? Basically this, right? You know, I need a minus on one of those or the other. I think the first one.
The top
Yeah.
side, I think.
Top one?
minus in the top
Okay.
right side.
Now he claims that this is obviously path connected. Why is this obviously path connected? What does it mean to be path connected?
To be continuous? I mean,
It's a continuous function.
I guess if you're just reading this book, maybe you don't know, because he hasn't carefully defined path connected yet, has he?
that I remember.
I think he's just treating it. I think he says in there he's just treating it as an intuitive concept. Let me give you a formal definition so we have a little bit more to go off of. Okay? It's not a big deal, Bradley, but
Definition of path.
But yeah, definition of path connected is that X is path connected if for any pair, say X and Y and X, there exists a continuous path from 0 to 1 to X such that alpha of 0 is X and alpha of 1 is Y. That's just what it sounds like. To say that a space is path connected means that there exists a path between any 2 points. Now, I have taken the path here to have interval 0, 1, but you can prove a series of technical lemmas which says you can replace that closed interval with any other closed interval you like without damaging it, or even the whole reals. Not that we've done that in topology, but we could. But we probably won't. But we could. But we probably won't. So like, if you give me two things in SO2, right? For example, let's say cosine theta 1 minus sine theta 1, right? Sine theta 1, cosine theta 1, and say another one. What would be a path between these? I mean, what he's arguing in the book is very intuitive and simple, and in the non-technical sense. But basically, the point is SO2 can be associated, of course, one-to-one correspondence with the unit circle, right? And so his point is if you have theta 1, right, and you have theta 2, then you just go from here to here in SO2, right?
Yeah.
So it's path connected. Because every rotation between theta 1 rotation and theta 2 rotation is also a rotation.
So that counts as a proof?
Well, you have to make the path. Well, yeah, so, I mean, it wouldn't be too hard. Like cosine of theta 1 plus t times theta 2 minus theta 1.
Okay, so you're like alpha t is cosine of, what do you say? Theta 1 plus t times theta 2 minus theta 1. And I'll call this thing Pac-Man. Okay, there you go. Indeed, that is a continuous. Now, we haven't proved that this is continuous in the technical sense of continuous, but trust me, it is. Once we give a careful definition of continuity here, it will be continuous. So it is a continuous path. And if we put in t equal to 0, we get theta 1. If you put t equals to 1, you get theta 2. And is it a rotation everywhere in between? Absolutely, because it's always something of the sine, cosine, minus sine, sine.
Right.
Which we see from the picture here.
Right.
So he just argues by the picture, basically.
Mm-hmm. Which is...
So, I mean, all he says is, for n equals 2, we have the circle, SO2, which is obviously path connected. So, in other words, another way of looking at it, what he's saying is that you have that the circle and SO2 are homeomorphic as topological spaces. They have the same topological structure. We know that the circle is path connected. So SO2 must also be path connected because topologically the same space. And path connectedness is a topological feature. It's a topological invariant. Anyway, there's an explicit proof, okay? All right. Now that's not it though. We want to prove SON is path connected.
Yeah.
So we just did the part he said it was obvious.
Induction.
Okay, so what's the argument? He says now, it is induction. He says now suppose that SON minus 1 is path connected and that A is an SON. So suppose inductively. A is an element of SON, right? He says it suffices to find a path in SON from the identity to A, because if there are paths from 1 to A and 1 to B, then there's also a path from A to B. Make sense? So like, think about that. If you've got an identity, right? And if you've got a path over to A, right? Some alpha. And if you've got some, and A is arbitrary, then you can also get a path to B, right? From 1 to B. Which means that you've got reversing that path and going that way, you've got a path from A to B, or B to A. So it suffices to look at how to connect the identity. If we can connect the identity to an arbitrary element, we're good to go. Okay? So that's a nice simplification brought to us by the group structure. All right, so we're looking, so he says this amounts to finding a continuous motion taking the basis vectors, E1 through En, to their final positions, A, E1 through A, En, the columns of A. All right, so he says, okay, so this right here, right? You can think of this in terms of what it does to the standard, so this is the usual standard, like x1 hat, x2 hat, so forth, right? So we're going to map this to what? To A, E1, A2, AEN, right? We also know from linear algebra, like, this is what?
Column 2.
Column 2 of A, right? Which, by the way, is what? By the way, what can we say about these columns? What is that?
You're also orthogonal.
Is Wang still in school?
As in he doesn't have a doctorate, or?
How does it at school?
We'll check.
In 2 hours.
Give a minute. All right, so this is where we are. All right. I will be right back.
I don't know how we're gonna go from calculating this n minus 1
Yeah, I know.
to getting it to n. It makes no sense to me. I'm assuming we're assuming everything up to n minus 1, right?
Yeah, we didn't say that, but I mean, okay. I'm not sure if that's
A break. Break to look at all his cool little books.
4:00 p.m.
No. Did you do anything on the other problem? The explicit mapping from what was it, SO3 to
Yeah, SU2 to SU3.
yeah, that's what it was.
Well, I went on to Wikipedia like you said, and I was like, I don't know what this is. So I kind of made it my own thing, but didn't really go all the way. So just, what did you do something?
Yeah, Wikipedia never helps me.
I'm back. Uh-oh. Something is amiss.
She let me get growth.
You can't go to Dr. Wang's office to around Chinese New Year night eat candy. Like, here, have some. Tradition. You have to accept.
What kind of candy did he give you?
Hershey's chocolate.
Oh.
It's not bad. All right, so what I was going to argue is these are orthogonal, right? So he says that the vectors E1 and AE1, if distinct, define a plane P. So by the path connectedness of SO2, we can move E1 continuously to the position AE1 by rotation R of P.
Oh.
Okay. And this here's E1, right? And I don't know, here's AE1, right? So those define some plane, which he calls P. And he said we can move E1 continuously to the position AE1 by rotation R of P. He says that then it suffices to continuously move RE2, REN to, alright, so he said this, I need another color. It's like this, so here, some rotation R, right? So continuously move R continuous rotation of E1 to AE1 by R, because that's in a plane, which is an SO2. But then what, he says we also need to continuously move RE2 up to REN to AE2 to AEN, respectively, keeping A1 fixed.
Which we can do with n-1.
Well, let's see here. He says, first of all, RE2 to REN are all orthogonal to RE1 because E1, E2 through EN are orthogonal and R preserves angles. I mean, that makes sense. If R is a rotation and E2 through EN is a standard basis, the orthogonality of the standard basis is preserved through rotation. Fine. And then he says, okay, so then AE2 through AEN are all orthogonal to AE1 because, as we talked about, A is an orthogonal matrix. And then I think what you're saying is next, Bradley. He says, thus the required motion can take place in the Rn-1 of the vectors orthogonal to AE1. Oh. And then RE2 to REN to AE2 to AEN gives a path from 1 to A in SON. It's been drawn.
Yeah.
Is one's the identity matrix?
Yeah, 1 is the identity. Yeah, exactly.
Right, so like the standard basis is like the different columns of one.
Right. Yeah. So basically, I mean, so this E1 continuously rotates to AE1 because you can fix the plane in which A and AE1 is in. And then what? But at that point, what have you done? You've taken, I mean, so here's a picture. You start with E1, E2, right, EN. You do this R, right? And that gives you this, AE1, right? But then also RE2, right? All the way out through REN, rather. That makes sense. Because R rotates E1 to AE1. And then his point is, okay, so if you want to fix this one, right? And then somewhere over there is the given columns of A, right? Like the A, E, N, and A, E2. They're somewhere else, right? But to get from so you can get from here to here and here to here by some continuous motion in the A1 perp, which is the SRN minus 1, and there's a continuous motion in there by the induction hypothesis because SON minus 1 is path connected. But we need to show that keeping AE1 fixed, right? Which is possible. So
We can keep A1 fixed because it's an orthogonal or orthogonal matrix.
because
You can
AE1
make a rotation about it.
because AE1 is perpendicular to AEN through AE2.
Right.
So it's in the perp.
Right. So it's just rotating.
I mean, in other words, this is the span of AEJ such that J is not equal to 1
Right.
because of the orthogonality of the columns of A. So any rotation of that space must fix what's not in the space, which would be AE1. I'm never quite satisfied with these proofs. I'm sorry, guys. I mean, I think it's a proof, but it's...
Seems good.
Okay, well, good. Seems good to you, good. I'll move on. Okay, so that's path connectedness for SON. Where did I put my cap? Oh, I see what happened here. Age-old problem. Then we'll get interrupted again. My wife is bringing traditional Chinese, I think, New Year's cake or something for Dr. Wang, so I'm going to have to go run down and get it, but that's okay. I think leaving for a second, coming back helps my thinking. All right, so next you can talk about the path connectedness of SUN. All right, path connectedness of SUN. Try to be more brief here if I can. He says, we can prove SUN is path connected along similar lines to the proof we just gave. Again, the proof is by induction on N. He says, but the case N equals 2 demands a little bit more thought. All right. I think I'll just look at the SU2 case and leave the induction to you guys. All right, so look at alpha minus beta, beta bar, alpha bar in SU2. All right. Then what do we have? We have that, he says we have the alpha and beta. Alpha comma beta is a unit vector. In C2, let's see why that is. So if you look at the length of alpha, beta squared, it's what? It's like alpha bar, beta bar, right? Dotted with alpha, beta. If you allow me this notation. I mean, in other words, it's alpha, alpha bar plus beta, beta bar, or you put it whatever you want, you know? Alpha bar, alpha. Now, of course, that's also what? That's also the determinant of this matrix, right? Which we assume to be 1. So that's why that has to be a unit vector in C2. So if alpha beta is a unit vector in C2, what's that mean? That means that you could write it, he claims here, as something like u cosine theta nu sine theta, where the magnitude of u and v, or nu, u and nu is both 1. So you could take u and v to be unimodular. I mean, okay, that's nothing. Well, how to say this? All right. Let's see here. So, in other words, you can write this as something like cosine theta e to the I. I need some other letter. Let's see, he uses a phi for this one, and a psi for the other one. Phi and psi being real constants. I suppose this makes sense because let's say this. Well, I mean, of course, any, I don't know. I kind of want to derive why this is, you know. So alpha is a complex number, right? Alpha is equal to what? So it's equal to the modulus of alpha times e to some, let's say I phi, right? And we also have beta is equal to the modulus of beta times e to the I psi, right? But you also have that alpha alpha bar plus beta beta bar is equal to 1. So what that becomes is modulus of alpha squared plus modulus of beta squared equals to 1. So that implies that there exists a theta in the reals such that alpha is equal to cosine theta and the modulus of beta is sine theta, basically. There is some choices of phase and stuff going on in here, but you know, up to a redefinition of these constants has to make that match. I mean, these modules should be positive, right? So how do I know that? How do I know that I've got the right? I guess it's just because there's a choice of angle, which makes this so. It's fine. The thing I'm worrying about is taken care of by the fact that these can be positive or negative and such. Okay, I'll shut up. Anyway, so there's that, right? So then what? If you've got two of these, it's then, right, if I've got two, or I guess we just need to connect to the identity, right? Let's learn our lesson from the abstract comment. Let's just connect. How do we get from to that? What's the path? I better not use alpha. Kind of a choice, right? Let's say, what do you guys want? F. Okay. Yeah, why not? So f of t equals to what? How about e to the I? Not quite working.
Well, the conjugates make it weird.
I mean, I could look at the matrix in terms of, I mean, there's a connection, right? There's a mapping that goes from here to here. I can either look at the SU2 as a 2x2 complex matrix, or I can look at it as a complex vector that satisfies this condition here, in some sense. So how do I get from here to there?
You could try to do something like we did with the other one.
I'm an idiot, yeah. I was almost on the right. I had to. You got to commit. You do something like you did in the other case, but you got to commit a little bit more here. It's cosine of t theta e to the I phi t, and then sine of t theta e to the I t psi. And then, the minus here and a sine t theta e to the minus I t psi, because it's the conjugate, right? And then down here you got yourself a cosine t theta e to the minus phi I phi t. If you look at this, of course, because of the structure here, it's always in SU2 because we have this relation conjugate. The diagonals related by conjugation like that, and then the off diagonals have the proper minus beta conjugate structure, so that this means that this is for each t between 0 and 1 in SU2, right? It's definitely in SU2. And also, if you plug in t equals to 0, well, cosine 0, 1, cosine 0, 1, exponential of 0 is 1, exponential of 0 is 1, but the signs kill these pieces. So 0, it's 1 and 1, so that's the identity map. When you put t equals to 1, you're back to this. And so there you have it. That's an arbitrary point, though, in SU2. So this shows that SU2 is path connected. I just for some reason, I wanted to just put the t up here, but like fix the theta, but that's not the right idea. He does say that the SU2 case is more involved. I have to agree. But there it is. Okay. Shall we on? Okay. Ooh, man, that would have made a nice advanced calculus problem, wouldn't it? Look at all these things I'm learning, but by the time I teach advanced calc again, I will forget these.
Yeah.
So, that's the sad thing. Alright, so the symplectic groups. Now we talk about these. We have now found our way to the doorstep of section 3.4, which is on the symplectic case. So I have threatened to present this in more detail. Now the time has come. So he's like, so basically in HN, if you look at quaternions P1, P2, Pn, and you want to define the dot product with Q1 through Qn, well, it's defined to be P1 Q1 quaternionic conjugate plus P2 Q2 quaternionic conjugate plus da 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 plus Pn Qn quaternionic conjugate. And he said, what he says is, of course this is formally the same as the inner product on Cn, except now they're quaternions, right? I mean, okay. He also warns against quaternionic matrices because the non-commutativity of the multiplication just spoils certain classical identities with determinants, right? So like it's not wise to try to use the quaternionic matrices to do things because it can be deceiving. So instead what people do is they look at the copy of this inside 2x2 complex matrices, right? So basically Hn you can look at as C2n, right? Or you can look at it as R4n. And so you can look at a version of the symplectic. There's some set of linear transformations which preserves this bilinear form, and those are called SPN. So SPN preserves that. Okay. So he points out, he says SP1 is just 1 by 1 quaternionic matrices which preserve the length in H. All right. In other words, SP1 are the unit quaternions. So let's look at the SP. Let's actually write that down. SP1 preserve this one. So what is it? P1 dot Q1, which would be P1 Q1 bar. So if let's say R is an element of SP1, that means that RP1 times R, I think I can just use P and Q now, right? RPQ conjugate, right, is equal to PQ conjugate. RQ. But this R is just a quaternion. So properties of quaternions are what? Remember the conjugate? We get P, we get Q bar, we get R bar, PQ bar. Something feels wrong. Something feels wrong about this. How did I end up with? I think the conjugate's supposed to be on the other side, right?
So it should be R conjugate P, Q conjugate R?
Yeah, if I had the other way around, right? If I had RP
Well, then it would.
conjugate times RQ equals to P conjugate Q, I think I'd be happier then.
But then it would. Oh, yeah.
So you could then, P. Oh, but it's still weird, right?
I mean,
So are you
you
here?
have the conjugate first.
Yeah, I can come down. I'll just be a second, okay?
Should there be a transpose somewhere?
Okay, bye-bye. She's outside.
Is it the conjugate transpose times something?
But this is, there's no, these are 1 by 1.
Oh.
We're talking about H1.
Right.
Yeah, so it's just good turn. Okay.
Wait, so it's so confusing now?
Oh, I'm trying to understand. He says, allegedly it's just this, right? So it's just these unit quaternions. And I believe that, I'm having trouble. Can you guys see if you can derive this from that condition somehow, then I'd be happy when I get back. All right?
From the condition of P dot Q
Yeah, try to explain to
equals-
me why unit quaternions are in fact just SP1. In other words, SP1 is exactly S3. The 3-sphere, right? I'll be right back, guys.
Dot P dot Q SU PQ conjugate. Vectors of A from I don't know where you got the conjugate from.
Which conjugate?
Where did this come from? That conjugate.
Is it part of the definition of the dot product for quaternions?
So he's just saying that
So P dot Q is equal to P dot, or just P times Q conjugate. So then we would look at RP dot RQ, which would just be RP times RQ conjugate, which would equal RP times Q conjugate R conjugate. And R.
I'm back. You guys figured it out? No?
So,
Can we go over the problems?
yeah, we have to look back at SU2.
My question is, why is SP1? Right, so SP1 assumably is the isometries. In other words, linear transformations which preserve this symplectic dot product. In the case of just one quaternion, so a pair of quaternions. So as I saw it,
So then we have to look at what we define quaternions to be in terms of, you can write it as complex matrix, right?
right, yeah. So if we look at quaternions as 2x2 complex matrices, then it's a little different. True. Fine, let's do that. Maybe
then-
productive. What is it? Was it?
The determinant of that thing has to equal 1.
Well, what's the 2x2 Well, yeah. What is the quaternion as a 2x2 complex matrix? So,
A plus ID.
so if I have A plus IB plus JC plus KD, that is, let's say, quote unquote, equal to what 2x2 complex matrix?
A plus ID in the top left. Then negative B minus IC, top right.
All right.
B minus IC, top, yeah. And then A minus ID.
All right. What is it?
So then the determinant of that, by definition, has to equal 1.
Well, I would. I mean, if that's my. Why would the determinant of that be 1? I mean, this is a point.
Because it's got a S in the name of the group.
This is like this is like the P up there. So my question is, what's analogous to the rotation times P here? I mean, well, okay, fine. The rotation is, after all, I mean, we're in H1, right? So that means that we're looking for a linear transformation from H1 to H1 again, right? Which preserves the dot product. But that means that L of P is just equal to RP for some R in H1, right? So I think what that also means then is, if I look at the corresponding motion, if I instead look at let's say L tilde viewed as a mapping from what's our notation for this? H1 as a 2x2 complex. I mean, what's our notation for? We just call it H1 again, right? But it's really not H1 again. It's the 2x2 complex matrix which models H1. I mean, what are these things